Hey everyone, welcome to the fourth video for section 3.7. So in this video, we're going to be talking about what are critically damped and overdamped solutions, what do they look like, how do they come about, and sort of what do they play in the role for all this different stuff. Let's go ahead and jump right into it. So critically and overdamped solutions basically come about when your damping coefficient gets bigger and bigger and bigger. So the underdamped case was when we had small damping, so gamma was small enough that things still oscillated. When you get to this case, things stop oscillating because your damping coefficient is too strong. So these show up as gamma gets bigger and bigger. And the way to sort of see where this transition happens is to look at the mu we had before. So our quasi-frequency mu was given by 1 minus gamma squared over 4km to the 1/2. Now, when gamma gets to the square root of 4km, then we start having problems because then mu goes to 0, which is no frequency. So what that means is you stop oscillating. When you don't have any frequency anymore, you stop oscillating. So as your frequency gets smaller and smaller, it starts drawing out your oscillation. It gets really, really far drawn out. And when it goes to 0, it means you don't oscillate anymore, which means you're going to go straight to the equilibrium solution, and that's about it. You're not going to oscillate back and forth forever. So when we get this equality, we're in case 2, which is the critically damped case, which is we get to the general solution is A plus BT times e to the negative gamma over 2m times t. So we're critically damped in this case. We only have one repeated root. And then if you keep pushing gamma further beyond that, you get to the overdamped case when you have two real roots, two distinct real roots, both of which are going to be negative. When we have more damping than being critically damped, we are what's called overdamped. And this is our general solution, being u of t is a e to the r1t plus b e to the r2t. r1, r2 are both negative, which means we're going to decay to 0. And we're not oscillating, we're just going straight to 0. We can't do any oscillation from there. It turns out if you have one of these solutions, you can cross 0 at most once, and that depends on your initial conditions. We'll see some examples that when I pull up the code, I'll make it so it ends up crossing 0 at some point so you can see that can happen if your initial conditions are such that it works that way. All right, so let's go ahead and pull up some Maple code where we'll show how these work along with the underdamped case from last time and see what I mean by all this stuff. All right, so here I have a very simple setup for this sort of problem. I've set the mass to be 1. We can set the mass to be 1 arbitrarily and just divide these constants by the mass. It's no big deal. So I have my k and my damping coefficient set up here. I also have it displaying this ratio of gamma squared but divided by 4k so we can see where that lands. When this gets to 1, that means we are at the point where we're critically damped. If it's less than 1, we're underdamped. If it's bigger than 1, we're overdamped. This is the way you can sort of check to see what situation you live in. So here's the ODE. It's second derivative plus gamma times the first derivative plus kx is 0. I have it solve the equation. I have us plug in our initial condition, which we'll change a little bit to see how it looks, and draw the curve. So in this case, if I have 1 and 1 as my two coefficients, my ratio is at 1/4, which means I'm underdamped. And you see, I get oscillation like this. It goes, it oscillates, it dies off pretty quickly, but it oscillates. Now we can compare this to, say, if we have no damping. We set this to be 0. So we change it to be 0, and now we get oscillation that just runs forever and doesn't decay off at all. We can also check some intermediate conditions to see what they look like as well. So if I check 0.1, I get decay still, but it's a lot slower than it was for the 0.5 case. And if I check 0.25, say, or 0.5, I get some intermediate level of decay there. Now we can throw all these together and see what they look like as a group, and you get this. Here are all of them put together. So the black is the 0 decay, the red was the 0.1, the green was the 0.5, and the blue was with 1 as a damping coefficient. Now as you can see, they decay off in the rate that they should. The blue goes away first, and the green and the red and the black stays constant. But you can also see this period shift, right? We said the frequency was basically, the ratio between the frequencies was 1 minus gamma squared over 4km squared, or square root. So as gamma gets bigger, the wave should start to slow down and have a larger frequency. And that you can see if you look at this second top peak here, if you look straight down, the peaks don't all line a line anymore. They're a little bit shifted to the side, right? The red's a little bit to the right, the green's further than that, and the blue's even further than that. So you get the shift in the period, or in the period of the frequency, based on this damping coefficient. So not only does the blue one go to 0 faster, it also has slower oscillation because of the damping coefficient that shows up in this setup. All right, so that's underdamped. Now what happens for critically or overdamped? What kind of things do we get there? So let's go back to black on this. Critically damped is going to mean that I need to put a 2 here. So I put a 2 there, I have 1, I get a solution that goes to 0 pretty much directly and doesn't do anything fancy about it, it just goes to 0 and decays off, and that's what we get. Also, it happens if we increase the damping coefficient further than that. So 2, let's see what happens at 4. Again, decay, but it's going a lot slower this time. And that's the main thing that characterizes critically damped. It will not oscillate, and it will go to the equilibrium solution as fast as possible. It'll go faster than any other solution. So if it's overdamped, it's going to take more time to get there because it's just going too slow because of the increased damping. So there's 4. What if I make it 8? Even slower still. We can even put those all side by side to show you what happens. So the black was critically damped, the red was overdamped, and blue is even more overdamped. As you can see, they're all just going right to 0, but they're going slower than the critically damped solution. And that's the point. That's the way you can characterize critically damped, is it is the fastest one to get to the equilibrium solution. I mentioned before the going past 0 business, in that the solution can only go past 0 at most once, and it has basic initial conditions. So let's take a look at stuff and see how that works. Let's go back to the critically damped case and see what happens. So let's start changing initial conditions. So if I want it to go past 0 at all, I need to sort of throw the weight down towards 0. So I need to make my D negative. So see if I do -1, what happens? It gets there faster, but it's still not going past 0. Now I can just overshoot this lot, which I'm going to, make it -10, and then we do go past 0. But you'll see we only go past 0 once. If you throw it really hard downward, it's going to shoot past 0, but then on the way back, it's just going to do its normal thing and go right to the equilibrium solution and not have any problems with that. This also holds for critically damped as well, so if I go to critically damped and say make it 4, it does the same thing. It shoots by, and then it goes right back to 0. No big deal. Now, underdamped, on the other hand, will oscillate, and this matters a lot more because you'll get a lot of amplitude out of your derivative as well. So if I make this, say, 1, which is underdamped, I'll get a pretty huge spike down there all the way down to -5. Because of the fact that it's going to keep oscillating, it's going to store all that energy and then dissipate it eventually over time. All right, so there are the main points for this video. So we're talking about what are critically overdamped solutions and then showing you pictures of how these all look like if you draw them out on graphs. In the next video, we're going to do a brief discussion of LRC circuits, which actually will see satisfy the same equation as the mass on a spring, which means we already know how to solve it. And then we'll do some examples of problems that you might be expected to see, things like that on exams and quizzes, that sort of thing. All right, thanks for watching, and I will see you in the next one.